In this video we're going to have more of a look at electromagnetic induction, and to start off we'll look at the definition as stated in the glossary of the syllabus. So it's another one of those key terms that you need to be able to basically reproduce almost word for word. And the definition is that it's the production of an electromotive force. And hopefully you can recall that an electromotive force is also known as a voltage. And if you can't, it's quite helpful that the definition actually includes that as well. This shorthand notation that we use is EMF. The syllabus has capital EMF, but you'll often see it as lowercase as well. So it also mentions that it is a voltage, and that's produced across an electrical conductor. Now that EMF is not just one that's established because you connect it to a battery or something like that. It's due to the interaction of that conductor with a magnetic field. And note here that it's a dynamic interaction, so that means that there's motion involved. And we'll have a look at how that EMF is induced. But before we do, let's just reiterate what that electromotive force is. Now, this definition, while it relates to the content that we're going through here with electromagnetic induction, keep in mind that it also relates back to Unit 1, where it's looking at electric circuits. So this definition is not specific to electromagnetic induction, but it's a definition that, again, is stated in the syllabus, and so one that you need to be able to reproduce. So it's a difference in potential that tends to give rise to an electric current. Now, in this video, we're not going to see an electric current, but in subsequent videos, we'll see that the EMF that's produced due to electromagnetic induction will produce an electric current. So there's the two definitions that are important for understanding electromagnetic induction. Let's have more of a look at exactly what that means. So to do that, we're going to look at a particular scenario and consider here that we're looking at charges moving through a B field. So by starting off with charges, we'll be able to reiterate some of the understanding developed in previous videos, and then tie that into electromagnetic induction. And be aware here as well that this is a very specific scenario that I'm referring to. So the directions involved will change depending on the orientation of the magnetic field, the movement of the conductor through the field, and so on and so forth. And some of those specifics will be developed in a little bit more detail in subsequent videos. In order to deal with this scenario though, again, we're going to set up a magnetic field between two poles with north on the left and south on the right. So the magnetic field then is directed to the right as shown by these magnetic field lines. And that would have a magnetic field strength of B. If we consider two charges where the top charge is going to be negative Q and the bottom charge is positive Q, and both charges are moving through that field with a velocity V, and to make it a little bit easier, we'll make that perpendicular to the field. Using the right-hand palm rule, we can identify that the path travelled by the positive charge is going to cause it to bend downwards and move in a circular path down through the field, whereas the negative charge is going to move the opposite way, and it will therefore be pushed up. So to briefly summarise that, positive charges, again in this specific scenario, will be pushed down, and negative charges will be pushed upwards. Now, if we had the field oriented in the opposite direction, that's going to have an effect on the directions that these charges move. So we'll just stick to this particular scenario and identify positive charges moving down and negative charges moving up. Now, if those charges were actually contained within a conductor, so we're not just looking at individual charges moving through space and through a magnetic field, we're now going to consider that these charges were contained within a conductor. And that conductor is still going to be moving through the magnetic field with a velocity v. What we will still see is that those charges are going to move the same way as we've identified in that diagram above. So what we can do here is identify that these charges being contained within a conductor, so if I now represent these charges being located within a conductor, at some later stage this conductor is going to be positioned over this region here, and that means that the conductor is going to have positive charges down the bottom, as represented by the green plus, and negative charges at the top, represented by the green minus. What we see is that the positive and negative charges will end up at opposite ends of the conductor. And this is where the EMF then comes into play, given that we have a separation of charges. So in that diagram above, positives down the bottom, negatives up the top, and an EMF is always going to be established whenever we have a separation of charges. So this separation of charges gives rise to an EMF. And that EMF will be established between the ends of the conductor, so that if we were to connect those two ends through an external circuit, what we would see then is a current flowing through that circuit. As I said, we'll deal with that in a bit more detail in coming videos to identify how it is that the current's produced. But ultimately that's the basics of how we get this EMF being produced due to the movement of a conductor through a magnetic field, or due to its dynamic interaction with the magnetic field. And in the next video, we'll tie electromagnetic induction back to magnetic flux, and we'll have a look at how magnetic flux impacts on the production of an EMF.